Albert, for having invited me to the workshop. It's in fact my first visit to Scotland, and I must say I'm absolutely impressed by the city of Edinburgh so far, and in fact also by the facilities here in this wonderful building of the base center. And I hope that notwithstanding the transatlantic news, you will be able to concentrate on mathematics.
Positivity.
Okay.
Positivity.
Okay. Monotonicity is in a way one step further than just positivity. It means that differences are positive, and higher order means that differences of differences are positive, and so on. So that's the connection. And yeah, let me start with some basic notions. We have some intervals. I is the product, and F is a real function. And we define the translation operators E sub H and the difference operator delta H. Just usual definition, I would say. And since the translations are commute with each other, so you also use delta H. And for any, there's a small mistake here, and it should be delta H0 of F, of course, so with an F. So that means an operator to the power 0 is the identity. But of course, if the H here is 0, then absolutely this is zero. Okay, for n, a vector of non-negative integers, and H, a vector of non-negative entries, I define this new notion delta Hn. It means that n1 times I take the difference operator in the direction of the first standard vector, and 2 times for the second with H2, and so on. So this is defined as soon as S and S plus, yeah, S. This is neat because I is an interval, so then everything is defined. And we first consider dimension 1, then the vector of integers is just integer, that would be positive. I is now a real interval, and we will also use immediately the sum function of. It will appear several times. And we assume it is for the start that I is the unit interval, so f a function. And for any t which is smaller than 1 and a positive h, and t of t plus nh is equal to 1, this is defined, and it's the usual thing, f of the t plus n times h minus n over 1, f of t plus n minus 1, and so on. At the very end, plus or minus f of t. And here we have already a connection with the sum function. It is this delta, as defined before, with the vector of only once, and the vector here, always the same component, f composed with the sum at the point t divided by n, and so on, at every place. The connection between univariate and multivariate monotonicity is strongly connected to this. If f is a univariate C infinity function, or just sufficiently often differentiable, then this condition that these differences still is a univariate function is non-negative for every positive h, equivalent with the nth derivative of f being non-negative. This follows from Fubini, more or less. I can explain it later on if somebody else. And it's a non-trivial connection effect.
I think you don't. Do you really need C infinity on the left side? Doesn't the left side give you C infinity automatically?
Excuse me, what?
Does the left-hand side not immediately give you C infinity?
So a fixed n.
Immediately, that's not so immediate. It's
Is n fixed or varying?
No, it must be for all them.
it's not immediate, I would say. I would
Give you convexity.
both, in fact, both directions are not totally trivial. For you, maybe. For you, not. I mean, for me, not trivial. And correspondingly, if f is a multivariate C infinity function, then there's this equivalence that the f, and now I introduce here a shorthand notation because I use it a couple of times. F with this vector of non-negative integers is just the corresponding multivariate partial derivative.
And these are both for all n, right? For all.
So this is for fixed n. For each h on the left-hand side is for each h on the right-hand side is
N is fixed.
n is fixed. Yeah, n is fixed. N or the vector n is fixed. Well, and the main definition to start with is this one. We have such an interval. We have vector n, which is not the zero vector, and I say that the function on this product of intervals is n increasing, n being this vector, if all these differences are non-negative for every s in the interval, for every h, for every p which is below n, but, and it's important, not zero. Because if I would allow p to be zero, then this would mean that the function itself should be non-negative, and this is absolutely not necessary. And in fact, it is not wanted even. You will see it later on. And then, of course, after what I said before, f for a C infinity function, f is n increasing if and only if all these partial derivatives are non-negative. They exist, of course, for or it again is enough to be sufficiently often differentiable.
So the order, the order here is coordinate wise.
No, f is the partial derivative.
No,
It's just a
for
yeah,
P and N.
okay, yeah, of course, yes, you are right. The order for a vector is coordinate wise, absolutely, yes. Okay, let's go back to the dimension 1, and then again n is just a natural number. F is 1 increasing if and only if it is just weakly increasing, and f is 2 increasing if it is increasing and convex. Let's go to the dimension 2. It's an example we will use several times. We look at the product minus a and the positive part of it, where a is a positive number. Then it is immediately clear that f is 1, 0 increasing. That means it is increasing in the first variable if the others are fixed, and the same one here. It is also 1, 1 increasing, and this is not so trivial. It will be shown later. But it is not 2, 2 increasing, because you simply have a counterexample. You can calculate this difference here at the point 0 with the step size root of a in both, and here 2 and 2. And the value is minus a, so it can't be. Okay, my first theorem here, a function on the half-open interval, non-negative, is n increasing, n at least 2, if and only if there exist uniquely determined coefficients, and a measure on the half-open interval, other measure of course, such that f has this representation. It is a polynomial plus a mixture, plus a mixture of these functions t minus a, positive part to the power n minus 1. The mixing is over R. This function is always continuous, and if n is bigger than 2, then it is n minus 2 times continuously differentiable. Consider, we can make this a little more precise in a way. Consider Kn to be just all function now on the closed unit interval, n increasing and being normalized by f of 1 equal 1. And these very special functions, fa of t, t minus a plus divided by 1 minus a for a less than 1, and f1 is the indicator function. And here I can draw a small picture. We have the unit square. We have here the number a. Then the function is fa is 0 here, and starts from here linearly to the point 1, 1. So this is the graph of fa. And you see already if a converges to 1, we get the indicator function of the right endpoint. Okay. Then this Kn is a Bauer simplex. That means it is compact, convex set in a Hausdorff topological vector space, where the kind locally convex space, where the Krein-Milman integral representation is unique and where the extreme points are closed. It sounds a bit complicated, but it is in a way the most wonderful situation for integral representations. Where it is finely homeomorphic to the set of probability measures on a compact set. You will never find something better anyway. Okay, and another corollary is the second one here. If I again go to the half open interval, or would also be the whole half line. If such a function is absolutely monotone, that means n increasing for every n, then it is analytic with non-negative coefficients. And a third corollary, if I take the intersection of all these kn's defined here, so all the functions which are absolutely monotone and normalized here in the endpoint, this is also a Bauer simplex, and the extreme points are the monomials and this one special endpoint function.
You topologize your collection of functions by pointwise convergence?
Pointwise.
Yeah.
Yeah, always. Well, I come to the multivariate case. First, some special situations in examples. The first one, I have functions on the intervals ij, and f is the tensor product of those. So simply given by this definition, then it is easy to see that the difference, this multi-difference, in fact, is also a product of the single differences for every p. And this implies for non-negative functions that f is, in this case, a vector n increasing if and only if each component is nj increasing. I think you have to add that none of the functions is really identically 0. Then one of the directions is for obvious reasons not. Okay. The second one is a kind of, this word is probably never used, hardly used, a tensor sum. So it's a sum of functions of the single variables. And then we have this relation. This multi-difference is the corresponding, so to speak, partial difference of the function fi if p is just a multiple of the unit. So if there's only one positive component in p, and it is 0 if p has more than one positive entry, because then simply everything vanishes. And so we can also here say f here without any restriction, f is n increasing if and only if it's each if j is nj increasing. Now a special example in dimension 2. I define f of s and t as this integral, the indicator function, and of s, and t minus a positive part. And well, this function here is just increasing. So it's one increasing. This function, as we saw, is two. Well, I didn't mention it, but of course, t minus a plus is increasing and convex. So it's a two increasing function. So as we just saw, that's the tensor product here of these two. So this is 1, 2 increasing. And if I mix this, all these definitions are stable under a convex cone, so to speak. So this result is, the whole result is also 1, 2 increasing. And if you make the calculation, it's as minimum t multiplied with t minus half the minimum. So it is 1, 2 increasing and not more. And in this case, I have also a picture made by Maple. And you can see here, if you fix an S and consider it as a function of, no, if you fix it t first and consider it as a function of S, then you have just an increasing function. But the other way around, if you fix S and you consider it as a function of t, you get an increasing and convex function. Okay, for n now in deep of positive natural numbers, at least 2. So this 2d is just the vector 2, 2, 2, 2 in every component. Yeah, we consider, in analogy to what we considered before, Kn, all the functions on the unit cube, non-negative, n increasing and normalized in the point in the left, in the upper corner. It should be 1. Obviously convex and compact. And I define En to be E with the vector n as the tensor product of these extreme points. And here I do not mean, very often one uses this as an abbreviation for the vector space generated, but here's just the set of tensor products. So the set of F1 tensor and so on to it. And this second theorem for n, at least 2 in each component Kn is also a Bauer simplex. And the extreme point are just these tensor products of the single ones, the one-dimensional ones. This is a complicated, the result is very easily stated. As you see, it's one-liner, but even in the printed version, the proof is about 7 pages. So it's quite hard to prove that.
So these are the monomials and the monomials with.
Yeah, you have the monomials and these integral parts, and in every component, of course, with possibly different in 1 and 2 and so on. Yeah. Okay. But I will not. I have not really found an abbreviation until now of the proof, so I will not talk about this. But we can look at an example. If in dimension 2, a function which is 2, 2 increasing has, of course, then this form. So rho is here an element in both rho 1 and rho 2 are in E2, of course, because we have here 2, 2. And well, there we have constants. I mean, the polynomial part is a constant plus then is t minus a plus. And if I now require maybe that f is vanishes on the 2 half axis, then I get in fact this integral representation where mu in this case then is a probability measure, a non-negative measure on this unit square, and fa is just this function where you have the picture here. Fa of s, f times fb of t, and you mix that. And now we consider a special important case, namely n is the 1 vector. In dimension 2, we can just write down all these possible differences. Delta H11 is this 4 term, are these 4 terms. And if I take delta 1, 0, I have the difference in the first one, first variable, and in the second. That's absolutely clear. And for general D, we have a corresponding formula. You take f of s plus h, and then first you take one h away as one only, and the other h, then you have only S2 and so on up to SD, and then you, yeah, it's here written here. The last one here in this group is this. Then you remove the h of and at two places, and so on and so on. At the very end, you get minus one plus or minus f of s. Why are these functions important? Well, if f is the distribution function of some measure, say on R on the space here, RD plus, then means this f of s is a new measure of the d-dimensional interval from 0 to s. Then this difference with h and with the vector 1 is just a mu of this half open interval. And well, the next theorem is a characterization of such function, of such distribution functions. Here and here, that's only in this at this place, the ij can be arbitrary, non-empty, not necessarily intervals, and like even plus or minus infinity may belong to them. And I is the product set now, not necessarily interval. Then I can prove this result. F is the distribution function of some measure on some measure on the closure in the compactified R bar to the power d, if and only if f is 1d increasing and right continuous. And this proof relies on the fact that a function f, which is non-negative, is 1d increasing if and only if it is completely monotone on the semigroup I with respect to the component-wise minimum. And this is a two-divisible semigroup, abelian, of course, if and only if it is a positive definite function on this I with the minimum. And so far, this is in fact the only way I know of to get hold of a measure. So given a function which is 1d increasing and right continuous, one is really to rely on these results. I never saw any other. Well, in dimension 1, any two increasing functions, that is increasing and convex, is of course right continuous, and it is continuous up with the exception of the right endpoint, perhaps. If a multivariate f is only 1d increasing, this need not be the case. Here's a simple counterexample. This is an increasing function, even a tensor product, of course, of two increase, and it is quite continuous. However, in some applications, the following result is usable. For every n in ND, so also if there are some ones, otherwise it's easier, each n increasing function is a pointwise limit of some net of n increasing right continuous functions. It's not necessary if the components are all at least 2, because then f is itself is right continuous. Yeah, now an application, I would say an interesting application, mean values or classical power mean values as distribution functions. We fix a vector of positive entries so far and real number t, and consider these power means for t not 0, and then the 3 special cases. M0 is the limit of this. If t goes to 0, it's a geometric mean. M infinity is the limit when x goes to, when t, that's a mistake, t goes to infinity, the maximum, and the minimum t goes to minus infinity. By the way, if t is negative and if one of the components is 0, then this mt of x is automatically 0. And this means that here what I claim here is only really completely correct if x has only positive entries. So for a non-constant x with positive entries, this function from R bar to the reals, t going to the mean value is continuous and strictly increasing from the minimum to the maximum. And if one of the xi's is 0, then of course this remains 0 up to the geometric mean, and then it increases, but it's unimportant. Well, these are non-negative functions, and a mean value one could imagine, since also, of course, in the vector 1, we have the value 1. These mean values are really possible candidates for distribution functions, the apostrophes of probability measures. So, are they? Well, that's this result. If I restrict the mean value mt to the unit cube, it is a distribution function if and only if t is in this interval, which is a little bit in the positive part, and then some discrete set 1 divided by d minus 2 up to 1/2, and then 1. And if you look, what does it mean for d equal to? Well, then it's in fact the complete interval from minus infinity to 1. How to prove this? Well, mt can be written as a composition of two functions. This ft has nothing to do with this one here over there. Sorry for that. So f is this function s to the 1 over t composed with this. And now the situation is very, it's easy in a way. If t is positive, then the sum of xi to the t is a tensor sum of increasing functions, hence it is 1D increasing. And we need to know which functions on R plus preserve this property. Well, this result was shown already almost 20 years ago by a woman from Argentine, Patricia Morillas. She proved more or less the following: I is an interval and in Rd and J in a real interval. You have two functions which can be composed. Then if G is 1D increasing and F is as a univariate function D increasing, then the composition is also 1D increasing. Her proof is absolutely a horror to read. It is unbelievable, and I only because at the time I was so much interested in this result, I really had to fight with myself to do it, and it took me, I think, almost 3 weeks to go through it. And in between, I also contacted her, and she sent me some more material. But after 3 weeks, I was convinced the result is correct. It has not been really taken up by many people because I think it's kind of a little bit not really obscure, but a journal which is not. But it's French. No, a journal in French language, but the articles in English, but it in Belgrade from Yugoslavia. I've forgotten that. Okay, but once I was convinced that the result is true, I tried to find a better proof, and sometimes I found a much shorter, much more transparent proof using Bernstein polynomials. Well, but I will not go in detail here. Let's apply this to the mean values. If t is 1 or 1/2 or 1/3, and so we have ft of s is just a power of s, and of course then and ft, this function is absolutely monotone, so n monotone for every n, and mt is then a distribution function because it is ft applied to a tensor sum of increasing function, which is trivially 1D increasing. What do we do for the other t's? Positive, less or equal 1, but not one of this set we considered before. So here, then we use derivatives. And we see that the case derivative has as the last constant here 1 over t minus k minus 1. And this should be positive up to d, up to k like d. And so that means if t is less than 1 over d minus 1, this is sufficient for ft to be d increasing. In fact, also necessary, and the t values greater than 1, they will be dealt with a little bit later. So we have some part of the result. Some part. Before considering mt for negative t, a small remark. Let alpha and beta be positive numbers, then xi to the minus alpha is increasing on the half-line. And x, again, a tensor sum is then 1d increasing on the half space here, the open half space. And with the beta, s to the minus beta is completely monotone. That means that s to minus s to the minus beta is absolutely monotone on the left half line. And now let t be negative, put alpha minus t and beta minus 1 over t. Then mtx is up to a constant. The composition of this one with minus something to the power minus beta. And so by theorem 5, it is a distribution function and 1t increasing. Well, now again, the sum functions will appear. An important supplement to theorem 5 by Morillas is the following: that I be an interval, or with non-degenerate, sigma the sum function, j the image of the all possible sums. Here, and f real value function here. Then, in fact, f is d increasing if and only if f composed with the sum is 1d increasing. And the non-trivial part here is, in fact, from the left to the right. That is theorem 5 applied to this situation, since the sum function is obviously 1d increasing. It's more or less the simplest tensor sum of increasing functions. No? For the other direction, it is sufficient to consider this interval 0, 1 over d to the power d, and then all the sum values are in the unit interval. We take a t less than 1 positive h such that t plus k times h is less than 1, k less or equal to d, and then I write again something which more or less was already at the screen before. This case difference of f with this width h is this multivariate difference. I have k times the 1, and so for the rest I have zeros here, and I have all these the same value here. F composed with the sum function at the point t over d, t over d. It's simple, but there's a caveat. We have to pay attention. We would need here at this in this moment that t divided by d plus h is less or equal to 1 over d, because we want to stay in the given interval, or t plus dh less or equal to 1, but we only know that t plus the smaller number k is less than or equal to 1. Well, there's a lemma which is easily proved. That, if you have any real interval and a function, and we know that these, we have just a k, a grade k, if there exists a positive number h0 such that these differences are non-negative for every h which is small, between 0 and this given h0, such that it is defined, then the same holds for all h. Not difficult, but important. In order to apply it here and to finish the proof of theorem 6, one would have to choose 1 minus t, which is positive, divided by d. Yeah, one coordinate. The function on the unit interval is well, I should have say, no, it's correct, that's a tense. It's d increasing if and only if f composed with the arithmetic mean is 1 d increasing. So if it's no negative distribution function, you might ask what, for example, if d is equal to 2, what is the measure of which it is the distribution function? Well, it is the one-dimensional Lebesgue measure divided by 2 on the bottom line and on the 2 axes. No. So we have again unit square, and we take this line and this line, and we take here half Lebesgue measure and here half Lebesgue measure, and then the distribution function at a certain point, because it's the measure of this, and this is simply then the sum. So it's x divided by 2 plus y divided by 2. Okay. Now a natural question. Suppose f is a two-dimensional distribution function of a probability measure. Let's say g is three-dimensional one, for which functions on the unit square is then always f composed with this concatenation or a five-dimensional distribution function. So apart from normalization, when is f of capital F of x, capital G of y, 1, 5 increasing? Well, the answer is given here. In a slightly more general, I have d higher dimensional intervals, I1 in R to the N1 and so on, ID in R to the ND. And I have functions from these intervals always into the unit interval. And they are all more or less distribution functions. So 1 and 1 and so on. They are all. And now, and this n now should be have these components, n1 up to nd. And then if f is n increasing, vector n increasing, then the composition is a distribution function 1. N and n in bars is the sum of the components. It's the L1 norm of this integer vector, yeah, the sum of the n j. Well, the proof is actually very simple now. We may assume that f is normalized, and we may also assume that it's not that completely clear, but let's do it here. N is, all the nj's are at least 2. Then by theorem 2, f has this unique integral representation on the extreme points of this our simplex kn for some probability measure mu on en. So f, if I insert these functions, then I get here an integral over the tensor products of rho I composed with gi. And each rho I composed with gi is 1 ni increasing by theorem 5, Morillas. Therefore, the tensor product is 1 with the sum of these ni increasing. And then f is a mixture of those, so it has the same monotonicity property. A special case would be that all these GIs are sums on suitable ni-dimensional intervals. And as a generalization of theorem 6, we have, and now I use this notation, sigma n vector is a concatenation sigma n1 and so on up to sigma nd. So the situation as before, I have an multi-dimensional intervals, I1 up to ID, and the sum values of these intervals are also one-dimensional intervals, ji. J should be the product of those, and f a function on j. Then we can indeed say that f is vector n increasing if and only if f composed with this special sum function is 1 norm n increasing. And finally, we get a natural generalization of theorem 5 that I would consider the first main result here today. Let GI on some interval ni dimensional be mi, so not only just one, so just any vector increasing. Mi is a vector in n to the ni. And again, I consider this concatenation of these functions that goes into the unit cube. And if f is increasing, so it's f is now a function of d variables, and I have is increasing with the norm of f1 in the first place and so on, then the composition of f with g has this index of monotonicity, just the concatenation of these vectors m1 up to md. That's a very general result. Yeah, just to look at an example, let's take, as I said in the when I mentioned this question, d is 2, n1 is 2, and 2 is 3. The first vector is 2, 4. The second vector is 3, 3, 2. If g1 bivariate is 2, 4 increasing, g2 trivariate is 3, 3, 2 increasing, and then f is the sum here is 6, the sum here is 8. F is 6,8 increasing, then f composed with these two functions is now 2, 4, 3, 3, 2 increasing as a function of 5 variables. And the proof actually is more or less the same. It's the idea is the same. I will not. It's a mixture of tensor products of functions where one knows. Well, actually, at the very end, I see that f composed with g with this sigma has this kind of increasingness, and this means that f times g without this sigma is increasing with these m1 up to md. Okay. Special cases, they were already there, but one should keep them in mind. If g is vector n increasing and f is a norm of this n increasing, then univariate, then f composed with g is n increasing, and just in one dimension, the composition of two n increasing functions is n increasing, if defined, of course, if the composition is defined. Now I come to another notion of k increasing functions, and now k is a natural number, not a vector, but in any dimension. I start with this observation. If I is a real interval, f is continuous here, and this is any continuity, only for a short moment, then, such iterated difference of order k is non-negative for all h where it is defined, is equivalent with that I can take for every step another positive number, delta h1, delta h2, up to delta hk, for all t in the interval, positive hi such that this is defined. This is the result of Boas and Widder in a paper from 1940. It's only the lemma 1 there. The main result is not more involved, but it's the first lemma, and it's in fact easy to see. But you need the continuity because otherwise you would only get it for rational positive hi. So, okay, now the second definition. I have any d-dimensional interval and a real-valued function and k a natural number that I call f k increasing, and k is now no longer a vector, just a natural number. If for every j from 1 up to k, for every non-negative vectors h1 up to hj, such as the differences are defined, this difference is non-negative. It's just what in dimension 1 would be equivalent with this one, but in higher dimension it's not, but it's quite natural definition. And for k equal 2, these functions are in fact known as ultramodular. You can find it in the literature. For d equal 1, it's the known definition we had before, just mentioned. But already for d equal 2, increasing convexity and being 2 increasing are incomparable properties. two examples on R2 plus, the product is increasing but not convex, and the Euclidean norm is convex, however not too increasing. Just a counterexample here, you take just this double difference of the Euclidean norm at the point 0, you get root 2 minus 2. So negative. But there is a surprisingly close connection now to n increasing function where n is the vector. That's this theorem. We have an interval and d and k are natural numbers. Then f is k increasing if and only if f is n increasing for every vector n whose length is positive and at most car. And this is highly non-trivial, in fact, to prove. It's not at all, it's perhaps this one what one would like to have, and I also tried for a long time to, but yeah, it's true, simply true. And furthermore, for every m and for every other m-dimensional interval j, and for every positive affine function from, what do I mean by positive affine? An affine function is a linear function in the translation. And positive only means that the linear function is positive. So that the linear part of the affine function maps the positive also into its of the one space into the other one. Only this is important. For every positive affine phi such that phi of j is an I, also the composition is k increasing. Then we have an easy corollary. If I is an interval d-dimensional B also, and I have a real valued function composed with the k, so composition of two k increasing function in this sense is also k increasing. Another lemma, if I have two intervals in different spaces, I have two non-negative k increasing function, then also the tensor product is k increasing and the product. And in case that I is equal to j, also the usual product is k increasing. So it's multiplicatively stable. Well, the proof at the end, maybe that's of interest, because here I used, in fact, such a linear positive map, namely sending RD to R2D simply by duplicating phi of x is xx. It's a linear positive map, and obviously phi of I is in I, it's a diagonal, and therefore the tensor product composed with this phi, that's the product is also okay. Examples. Each monomial, obviously, is absolutely monotone on R plus or RD plus. And if I have non-integer exponents positive, then it's k increasing, at least if k is not larger than any of these ci plus 1. And now we are back to this function we considered already in the beginning. This function here, f of xy minus a plus, we saw, well, we knew that it's 2 increasing. Well, now it's 2 increasing as a function of 2 variables, since c minus a plus is 2 increasing on r plus. So it's a composition of 2, then xy minus a is, of course, xy is a tensor product and minus a, so we could already get negative values, which doesn't no, well, it's no, if I subtract a constant, it doesn't change anything with the difference. So by theorem 10 now, which just was there, f is in fact 1 increasing, which we didn't know before, and we knew that it is not 2 increasing, it is not even 1 increasing because of this counterexample here. The tensor product x minus a plus times y minus b plus is, of course, 2 increasing, hence certainly 2 increasing, but not 3 increasing, since the x to x minus a plus is not 3 increasing. I go one step further. X, y, z minus a plus squared is 3 increasing on R3 plus, and if I fix z to b1, I have a 3 increasing function on R2 plus. And here maybe an interesting example also, x on the unit cube, xy plus xz plus yz minus the product of the 3. And here these f1s, that's the partial derivative. F1 is non-negative. F11 is, of course, 0. F12 is 1 minus that is also non-negative. But if I take the third derivative, then I have -1. So f is 2 increasing, but not 3 increasing. A short intermezzo, Bernstein polynomials. I mentioned them already, and I will now use them for proving the main theorem here in this connection. That's the definition of these monomials here. And here I have the d-dimensional Bernstein polynomials, just the tensor products of the single ones. And for any f of the unit cube or box, whatever, the associated Bernstein polynomials f1, f2 are defined in this way. This you probably know. What you might not know that for each, I didn't, that for each continuity point of f we have that the Bernstein polynomials converge. Usually one only uses that they are converged uniformly if the function f is continuous. But here, I only pick a particular point, and this is very important here. And the proof is the best proof is via the strong law of large numbers. And this is not only true in one dimension, also in d dimension. And what I now will use is the upper right boundary of this d-dimensional cube. I define T alpha as those vectors where xi is less than 1 exactly if I is in the set alpha, any subset of 1 up to d. Then we have a disjoint union where T, the empty set, is just the left endpoint, left, and T with the full set is the product of the half opening. And if I take this away, all the rest is I will call the upper right boundary. And you will get the third time here. So this one here is this exactly from here. It's not. This is T with where the alpha is 1, and here we have T where the alpha is 2, and the interior here is T with 1, 2, and this one here, this point is T with the empty set, and the union of those is called the upper right boundary of this unit cube. And why is this important here? Well, it is easy to show that on each part as just defined of this boundary, the restriction of the function, so this part has as its Bernstein polynomials, the restrictions of the original ones to this set. This is important because now we have the following lemma. If f on the unit cube has the property that each restriction to such a part is continuous, then the Bernstein polynomials converge pointwise everywhere. Because in this one last point which remains, they have they have the same value, and whereas in all the other parts we have continuity, and we use this result here. The Bernstein polynomials will remain the right ones, so to speak. And one lemma: if I have any function of d variables which is 2 increasing, then it is continuous if it is continuous in 1D, and it is always right continuous and in the interior continuous. So this means that 2 increasing functions are of the type of lemma 3, where we could apply what is necessary. Yeah, and then, okay, this is also not really trivial, but it's easy to see. If f is n increasing, then each Bernstein polynomial is also n increasing, and we have this pointwise convergence. It's the same for k increasing functions. Here I suppose that n has all components at least 2, and also k is at least 2. And now we can tackle another natural question of the preservation of monotonicity. If we have distribution functions on some d-dimensional interval, and now we use another type of putting these functions together, we have the same variable for each gi. So g of s is just g1 of s, g2 of s, and so on. Now the question, which functions on this m-dimensional cube preserve this property of being a distribution function? If f is for d equal 1, this is f is just to be increasing and right continuous perhaps, and for d equal 2 it is not sufficient IO. And here I can state the second main result. If I have a function on the m-dimensional cube, it is d increasing and d is at least 2, and I have g1 up to gm, say on the all of Rd distribution functions of automatically sub-probability measures, then also f composed with g1 up to gm is a distribution function. That's hard to prove, and the reason is this first step, which I only say very shortly what it is. The right continuity, of course, is given, and the crucial point is to show that the composition, H is here not a positive vector, but the composition of F and G, that this is 1D increasing. And because of theorem 11 just before, we may assume that F is from the outset a C infinity function. And yeah, this is the main part, the very complicated and explicit generalization of the usual multivariate chain rule and of Faraday-Brunus formula, which was published in 1996 by two statisticians, I think, in the Transactions of the American Mathematical Society. Constantine is one and Savitz is the other one. It's very, very complicated. You have index sets with which are horrible in a way, but it can be done. So this is really the hard work here, which I will. And then the second part is then very easy. If I have any, to finish the proof, I have an x and now xi, because h is now a function, and I have to show that this difference is non-negative. It is easy to find C infinity distribution functions which coincide with G as the given ones on a given finite set. And B, this finite set is X plus all these possible finite sums of psi I, E, in all the directions using this vector psi. And then I know, because of part one, I know here that this is justified, and G1 is simply the same as H on this finite set. So I have the proof. I will skip this because I also want to, that's my last short part, two related notions of monotonicity. Now I use the negative delta, which I will call nabla, and I say that's the definition 3, that the function f is n decreasing if all these nabla differences are non-negative, and it is n alternating if all these nabla differences are not positive. And then these remarks are simple but very, very useful. F is n decreasing on I if and only if f of minus is n increasing on minus I. And f is n alternating on I if and only minus f of minus is n increasing on minus I. And for a C infinity function, you can express this again with derivatives. For d equal 1, we have already mentioned this. F is 2 increasing if it is increasing and convex. It is 2 decreasing if it is decreasing and convex. And F is 2 alternating if it is increasing and concave. And F, non-negative F, is n alternating for all n. So infinitely alternating if it's a Bernstein function. So possible discontinuity point at 0. And an easy consequence of theorem 1 is this quite well-known theorem of Williamson. I take here the half line to avoid the discontinuity at 0. such a function is n decreasing n at least 2 if it has this unique integral representation. And by the way, n in one dimension, n decreasing functions are very often called just n monotone. But monotone is, I like much more to work with decreasing and increasing, but monotone can be, the direction is not always clear. And a more recent generalization is to larger dimensions. Yeah, and here an interesting appearance of 3 alternating functions. It is an inequality for real numbers, which was shown by Hornig and Lafka from Austria. You have any 3 numbers, then the x plus y, absolute y plus z, z plus z is less or equal always than the sum of these 3 and the absolute value of the sum of the 3. And this can be generalized. Let f be a non-negative 3 alternating function. Then this is the same holds if instead of the identity, which is here unwritten, I put an f everywhere. Yeah, f ID gives the original inequality, which also holds for vectors in the Euclidean space, so in particular for complex numbers as well. But this generalization here for vectors, I could show for the square root, for the 4th root, for the 8th root, and so on, but it is really open for any other Bernstein function. I mean, 3, instead of just 3, alternating, you can take Bernstein functions. You would expect, for example, for the logarithm, but there's no way. First, I thought one should easily come from these roots to the logarithm. It's unfortunately not true. And just here, a nice example. I found this in a paper in some years ago. This function defined here, minus log of 1 minus I to the minus t, they needed in this paper that it's completely monotone. That means n decreasing for every n. And this was shown in a rather complicated way by using so-called Eulerian numbers of permutations. But here we can prove it very easily. Phi of minus is minus log 1 minus composed with the exponential function. The Bernstein function is infinitely, so it's n alternating. So minus log of 1 minus is n increasing on the negative half line. The exponential function is wherever n increasing. So the composition is n increasing. And then phi of minus is n increasing. So phi itself is n decreasing for every n. So it's completely monotone. And again, of special importance is, of course, the vector with only ones. Non-negative 1D decreasing functions are essentially survival functions of measures of this form for some measure. And 1D alternating functions are essentially co-survival functions. It is of the complement of this, and even of infinite measures. This makes sense. And the particular subclass is connected with extreme value analysis. A distribution function on RD plus is called a simple multivariate extreme value distribution if it fulfills this functional equation, and it has standard Fréchet margins defined by the one-dimensional distribution function written here. And the minus log of f of 1 over x, where 1 over x is component-wise, is called a stable tail dependence function. It's a big rule in the extreme value theory. It is a function of the orthant to the half-line with the property that it's homogeneous, normalized. F is always between the maximum and sum. This would imply, by the way, this one. And it is convex. But this is a full characterization only for d equal 2. In higher dimensions, this was an open problem for many years. And I could then prove a full characterization. It has to be 1D alternating. That's the essential thing. It should be fulfilled. The rest is trivial. In this case, this function has a unique integral representation in terms of these maximum functions, where nu is a probability measure on the, in fact, on the upper boundary, which I used in another connection, on the upper boundary of the unit cube. The maximum of the Ci is 1. It's just another description of the upper right boundary and the classical norms. And now I can really, I spoke about the mean values, and the values for t bigger than 1, they now appear. That there are these classical norms here for p at least 1 up to the limit, which is the maximum. Then they are stable tail dependent function goes back to the mathematician statistician Gumbel. And here we have another type, for example. And okay, which univariate functions preserve n increase, and this is very easy. It follows from whatever I said. And that's my last one. I finish with an open problem. Quite intriguing, in fact. I look at the simplest example of k increasing functions, which is a non-trivial, on the unit square, normalized, and it should be just 2 increasing. It's compact, convex, and also multiplicatively stable, as we saw. I do not know if it's a Bauer simplex, and I would like to determine the extreme points. I could prove, and already this is everything but trivial. If I take these functions, which I defined at the beginning, these functions which f, a, f, b, f, b, if I compose one of them with the tensor product of the other one, then these functions are in fact extreme points, but that's all for the time being. So if anyone would have any idea on that, I would be very glad. Thank you very much for your attention.
Questions? Comments?
Yeah.
Are there Jensen type inequalities